this formula, which gives us the indefinite integral of polynomials? Are we talking about how it was established and what it actually tells us? This formula is what we use for integration of polynomials. It gives us what we call the antiderivative of a function. Integration is the reverse operation of differentiation. You need to remember this as we go into our next section. So integration and differentiation are inverse operations, continuing the pattern of operations in maths being opposites, like addition and subtraction, multiplication and division. Now we have differentiation and integration. So how do we know that these are opposites? Well, we know that the general equation for differentiation is x to the n. You bring the power out the front multiplying by n, and you subtract 1. So what we're doing is we have the original function, we're multiplying by its power, and then we're subtracting 1 from the original power. You can clearly see that integration is the opposite of this. When looking at its formula, you're having the original equation, you're adding 1 to the power, and then you're dividing by the power plus 1. Dividing by this power plus 1 reverses the process of multiplying by that power. And adding 1 to the power is reversing the process of subtracting 1 from the power, bringing us back to this same stage. From pointing it out like this, you can easily see that they are the exact reverse processes. There's one more thing that saw in the first equation. The first equation was x to the n plus 1 over n plus 1 plus c. So why did they have the plus c there? This is because if you differentiate a constant, you end up equaling 0. So if I have this constant here, 4, it's always going to equal 0 when differentiated, same as 300. So I'll show you exactly why we need plus c by differentiating these equations. If we differentiate x squared, it'll equal 2x. X squared plus 4, 2x plus 0, which is just 2x. And x squared plus 300 is 2x plus 0. These all end up equaling the same thing, even though they're all different functions. So if we went to integrate these and turn them back to their original equations, we'd go 2x to the 1 plus 1 is 2, divided by 2 is just x squared. Same here, it'd be x squared and x squared. They're all going to end up being the same function, which isn't correct. This is why we add the plus c for that constant, just in case it's there, so we can tell our functions apart. It's the plus c variable which stands in for them. So now we know why we've got this part of our function is just the reverse of our differentiation equation, and why we got our plus c for those constants in case the variable has gone missing. We have one more thing to talk about. When you're looking at the equation x to the n plus 1 over n plus 1, you can see that n can never equal to negative 1. This is because you cannot have the denominator of a fraction equal to 0. Therefore, if n is equal to negative 1, you always have to use a different formula and avoid using this one. So you can see exactly where this formula has come from. But what's it actually telling us, and how can we use it for real life scenarios? Well, if we look at this graph, we have this quadratic function. We can look at the graph and state its gradient being positive here, 0 here, and negative here. But unlike a linear equation where we know the gradient the whole way along the line, we actually don't have a way of just looking at points and being able to know their gradient. This is where the derivative comes in. It gives us the function of the rate of change at all times for polynomials. So if we look at x cubed is the function in red, and then 3x squared is derivative, this derivative is actually the function of the rate of change of the original function. So we're talking about gradient of a function. When we've talked about gradient in the past, we've always used the equation rise over run, or point y2 minus y1 over x2 minus x1 is equal to this gradient. To find our gradient for this, I've drawn up a graph. We have a and a plus h, and then putting them into our function to get our y coordinates. In a moment, I will show you how we can sub these in and get a gradient for our rate of change. So using this equation gives us our average rate of change, our average gradient. So I've subbed our points in, and now we have this equation here, which will give us our average rate of change of a function. You can put in any 2 points, and this will always work. But what we actually are wanting is we're wanting to have an equation that gives us the rate of change at any set point. This means that we have to make this distance between here 0 because we want the separate point, but it cannot equal exactly 0. So what we do is we set a limit of h approaching 0, making this infinitely small and meaning that we do have the equation for each individual point. If we sub this and add it to this equation, we get this equation up here, the limit of h to 0, and then this equation here. I've just subbed in x where the a's were for this example. So our original function is going to be 4x squared. I'm going to show you what happens when you sub this into the equation and how it finds us the derivative. So what it does is it subs that equation in up the top before they expand all of the values, still leaving h as it is and not subbing in 0. First, we have to cancel out some factors, so you're left with a bit. Then you sub in 0 where h was, and you get left with 8x. Now, we can double check this, knowing our equation already is n to the x to the n minus 1. If we have n to the x n minus 1, we have 4x squared. You're going to put n to the front. You've already got 4 there, so 2 times 4 is 8. So you're going to have 8x to 2 minus 1 is 8, just 8x, which is exactly what we got. So we can see that this equation's working. Now, if you didn't already have that derivative equation supplied, you could go through and differentiate using the first principles, which is what that equation was called, and see that the same pattern happens for all these equations. You can see that they're bringing power to the front and subtracting 1 from that original power, showing that we can always use the equation x to the n multiplied by m, subtracting 1 from that original power. This also verifies that we can use the integration equation, which is the opposite of this, to undo this process. So how can we put this into a real-life example? I'm going to use displacement, velocity, and acceleration as my example. Velocity is just the rate of change of displacement, and acceleration is just the rate of change of velocity. So if we want to find the rate of change of something, going from displacement to velocity, we just learned that you're just finding the derivative of that function. So we're just using our equation n to the x n minus 1. Going from velocity acceleration, you're doing exactly the same thing. You're finding the rate of change. So you're just doing d over dx again. Now, we know how to go up to rate of change formulas, but what if you have the formula for a rate of change and you want to get back to the original function? This is where your integration formula, x to the n plus 1 over n plus 1 plus c, comes in handy, because we can have our equation for acceleration, and using this, finding the integral of x to the n dx, and you're back to your velocity equation, same as if you have your velocity equation and you want to go back to displacement, doing the opposite of differentiating. You're going to integrate it with that same formula, and you'll be left with that original equation again. Having this integration equation just means that we can go back from what we've done when differentiating to find rate of change formulas. So now we know exactly where this is stemmed from and how it relates to real-life examples and differentiation. I'm going to show you a few examples of how we can use this equation. So we have our equation, the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c. Don't forget the plus c. So our first example is going to be 10x plus 2. So we're going to find the integral of 10x plus 2 dx. What we're going to do first is we're going to set this out, 10x. We're adding 1 to the power. It's just power of 1 and adding 1 plus 1, dividing by that new power, which is 1 plus 1. Now we're doing the 2. So when you've got 2, it's actually just 2 times x to the 0, because x to the 0 will always equal 1. So what we're doing here is we're going 2x to the 0 plus 1 over 0 plus 1, and don't forget your plus c. This is going to equal 10 over 2, which is 5x to the 1 plus 1, which is 2, plus 2x to the 1 over 1, which is just 2x, plus c, giving us our equation after integration. Our second example is going to be 9x to the 8. We're finding the integral of 9x to the 8 dx. So this is going to equal, we're going to have 9x to the 8 plus 1 over 8 plus 1. This is going to equal 9 over 9. Our 9's cancel. It's just going to be x to the 9, simplifying to this, plus c. Don't forget your plus c's. Awesome. Thank you so much for listening.